This is Dr. Mahesh Kalyan Shetty, Associate Professor, Department of Civil Engineering, Walchand Institute of Technology, Solapur. In this session, we will discuss about the analysis of indeterminate structure by moment distribution method. Specifically, we will focus on non-sway frames. The learning outcome of this session will be, at the end of this session, the students will be able to analyze the non-sway frames using moment distribution method. Let us take an example. Analyze the frame as shown in figure by moment distribution method, and EI is constant for all the members. So in this figure you can see a member AB, BC, CD and CE, and we have hinge supports at D and E and fixed support at A. The loading UDL intensity is 45 kN per meter and the point load of 60 kN is present at B. Now let us discuss how the analysis is to be carried out for this non-sway frame. Now this is non-sway frame, whereas you can see here the sway of the frame is been restricted by this support. Therefore it is called non-sway frame. Otherwise, if you don't have any restrictions in the lateral direction, the frame will sway, and in that case we need to go for a separate method of sway analysis that we'll see in the further sessions. Now let us begin with the analysis. As usual, first of all we have to calculate the stiffness of the member and joints. So we have two interior joints here, B and C, which have got the distribution factors. So therefore the stiffness of B and C is to be calculated. So at joint B, we know that two members are meeting, BA and BC, and the stiffness of BA and BC will be 4 EI by L, because it is opposite end is fixed here for BA, and for BC it is interior support, therefore it's 4 EI by L, and therefore the stiffness of the joint B is summation, that is KBA plus KBC. Same for joint C, we will calculate CB will have 4 EI by L and CE will have 3 EI by L. Now you can see here the opposite end is hinge, therefore CE will be 3 EI by L, and also CD will be 3 EI by L. So CD is 3 EI by L, CE is 3 EI by L, whereas CB is 4 EI by L. So the three members are actually meeting at joint C. Therefore the summation of all these stiffnesses will give me a total stiffness of joint C, that is summation. Then we will calculate the distribution factors. For joint B, the distribution factor BA is the stiffness of BA divided by stiffness of joint B, which comes out to be 0.545. For BC, again it's actually by this method also we can calculate, as already we discussed that the summation of all the distribution factor at any joint is always equal to 1. So we have only two members meeting at joint B, and out of that one member has got 0.545. Therefore the remaining next member is, naturally it is 1 minus 0.545, that is 0.455. Then joint C, again we have the three members. CB, it is coming 0.330, CD it is coming 0.298, and CE is coming 0.372. As per our usual notations, these are the distribution factors at joint C. Then the fixed end moments we need to calculate. So the member AB, since we don't have any load on this member, it is 0. Now member BC, we have the UDL, so we know that it's WL square by 12. So left side it is minus, since it is anti-clockwise. So FEMBC is minus 135 and FEMCB is plus 135. And the member CE, again we don't have any load here, therefore this has got fixed end moment 0. And member CD also no load is there, therefore the fixed end moment is 0. Let us take a pause and answer this question. Sway in the frames are produced due to unsymmetrical support conditions, unsymmetrical loading conditions, unsymmetrical geometrical conditions, all of the above. Think over it, get the answer and resume the video. Welcome back. Now this is the question asked, sway in the frame are produced due to. The correct answer is all of the above, because due to unsymmetry of all these, either it may be a support conditions, it may be a loading conditions, it may be a geometrical conditions, any one kind of unsymmetry will lead to sway in the frame. Therefore D is the correct answer. Let us continue with the problem. Now the most important thing is this moment distribution table. So already we determined the distribution factor of all the members, and the fixed time moments also is calculated. So this is to be arranged in this table. So joints A, B, C, D, E, the members will write here, and the distribution factor member B we calculated as 0.545 and 0.455, and for C we have three members and all the three distribution factors we calculated, which are written here. Then the fixed time moments, as we discussed, that only for BC member the fixed time moment is present, rest all it is 0. So only BC and CB the fixed time moments are present. After writing all these things, then we shall proceed with the distribution. So it is minus 135 is the unbalanced moment, therefore it is to be balanced here as per their distribution factor. Here also it is 135 unbalanced, so minus 135 we need to apply. Out of minus 135, 0.33 fraction is developed here, 0.298 fraction is transferred here, and 0.372 fraction is transferred here. And then the carryover will take place. So carryover from B to A is possible, as well as from B to C also is possible. So you can see here the carryover is possible. So this carryover will take place. Now this carryover will disturb the joints again, and again we will go for the distribution, because minus 22.3 is the unbalanced moment produced now. This is to be balanced, therefore plus 22.3 is to be applied as per the distribution factors. We distribute it here, and here also minus 30.7 is to be applied, and as per the distribution factor it is to be distributed. In this way we will continue with number of iterations, and once we get a very fractional value we will stop. So after 3-4 iterations it is observed that the process is over. Then they take a summation of all these members, so AB, BA, BC, CB, CD and CE, all the summations we can take it here. These are the final moments of the members, and these we can represent here with the help of this free body diagram. Now you can see here the vertical member, the members, the moment is 44.5 here, then 89.1, okay, then here 89.1 as per their sign. So if the moment is positive there, we shall show the clockwise moment. If the moment is anti-clockwise, we shall show it anti-clockwise. Sorry, if the moment is negative, we shall show it anti-clockwise. In this way, as per our sign convention, these free body diagrams are shown here. Now there is no moment at D and E. As you can see, D is hinged and E also is hinged. Therefore, there is no moment transferred here. So with the help of this free body diagram, now we have to draw the bending moment diagram. So the bending moment diagram, before that we'll just look at this free body diagram. Accordingly, we'll draw the bending moment diagram. Now you can see here, now one sign convention we follow here. If the moments are producing the tension outside, we take it as negative. If the moments are producing tension inside, we take it as a positive moment. So here you can see at A the moment is creating tension inside, therefore it is a positive moment, 44.5, and here you can see this moment is creating a tension outside, therefore it is taken as negative 89.1 here, you can see here. Same the case here. So here this also is negative, this also is negative, so both are hogging. So hogging moments are shown here, and in between, due to this UDL, we get a positive moment. So the maximum positive moment we get 101 kilonewton-meter, and here also for this member CE, the negative moment is produced here. This is hogging, and here also the tension outside, therefore it is minus, and then it is 0. At D the moment is 0, at E also the moment is 0. In this way we will construct the bending moment diagram. These are the references which are used for this presentation. Thank you. Thank you very much.